Hello.
Hello.
Okay, can you hear me well?
Yes, I can.
Okay, good. So we are going to go over chapter 4. I don't know if you have any question so far before we start. Anyone has a question on anything?
Nope, not yet.
Okay. So we are going to go over chapter 4. If along the line you have a question, just stop me, ask your question. Chapter 1, 2, and 3 was about descriptive statistics. We learned how to collect, organize, summarize, and present data. In chapter 4, 5, and 6, we are going to learn about some elements of probability, which are useful in making inferential statistics. So probability is a measure of uncertainty. So we try to associate a number to a random event. So probability is the process of associating to a random event a number. For example, when we think about weather tomorrow, whether it will rain or it will snow, we can say with a probability of 60%. This number by rule is between 0 and 1 or expressed as a percentage. So there are generally 3 types of probability. Intuitive probability, which is also called subjective probability, which is based on an individual intuition or feelings about a situation. For example, you may feel like there is a 90% chance that it will rain today, based on no calculation, just how you feel. There is also empirical probability, or which is also called relative frequency probability. That is what we did in constructing a frequency distribution table. In empirical probability, we make use of a random sample and then using the relative frequency to express probability. We also have classical probability, which is based on a equally likely outcome of a random experiment. We are going to learn this last one in this chapter. So for example, if a sport announcer claims that Sheila has a 90% chance of breaking the world record in the 100-yard dash, this will be an example of intuitive probability. If we use Henry figures that if he guesses on a true and false question, the probability of getting it right is 0.5. This is an example of classical probability because you have only 2 possibilities and one of them is getting it right, or getting it true, or getting it right, or getting it false. So this is an example of classical probability. Just like when you toss a coin, if you decide to toss a coin like 20 times and count the number of heads, you might get 12 heads, and that will mean that 12 out of 20, which is 60% of head, that is a relative frequency probability or empirical probability. But if you just know that when you toss a coin, there are 2 possibilities, that is head or tail, and one of them, each of them is equally likely to occur. So one of them is head, then the probability of getting head is 1/2. That type of probability is called classical probability. That is the comparison between classical and relative frequency. Classical probability is also referred to as theoretical probability. It's fixed, it doesn't change. Meanwhile, relative frequency probability changes depending on the sample that you have. I can toss my own coin 20 times and I get 10 heads. You toss coin 20 times, you get 8 heads. Someone else tossed it 20 times, you get 9 heads. Each of us will have a relative frequency of the number of heads that you get, and then it will be a relative frequency probability. The right to health lobby claims that the probability of getting an erroneous medical laboratory report is 0.4, based on a random sample of 200 laboratory reports, of which 80 were erroneous. So this is based on an experiment, and this result is empirical probability, which is based on a sample, a random sample. So I have explained what is empirical probability and what is theoretical probability, which is also called classical probability. So the main difference between them is that in a relative frequency probability, we don't always have the same answer. It depends on the sample that you are using. The law of large number comes to settle the difference between empirical probability and classical probability by stating that if you have a very large number of trials in empirical probability, your result will come very close to empirical probability. Meaning that if you play around with coin and you toss it 20 times, 50 times, 100 times, the larger the number of tosses, the closer the number of heads will be to half. So that is called in probability the law of large numbers. It also tells us that for very large sample size, we get a better reflection of the actual probability by increasing the sample size. So a probability experiment is a random experiment leading to equally likely, well-defined outcomes. Essentially, we say that it's an experiment in which we cannot predict what the outcome it will be, what the outcome will be, but yet we have equally likely outcomes. For example, when you toss a coin, when you roll a die, you can have 6 equally likely numbers. When you are drawing a card from a standard deck of 52 cards, you have equally likely outcome. Selecting a random sample from a population. A random sample is a sample that is representative of the population, so all random samples are equally likely. This is how we are going to connect probability to statistics, by considering random samples as equally likely outcome of a random experiment. So what we will call a sample space will be the set of all possible outcomes of a probability experiment. In tossing a coin, we have head or tail. An event is any portion of a sample space. So tail can be an event. When you toss a coin, having a tail is an event. When you roll a die, you can have a number 1, 2, 3, 4, 5, 6. If you want those numbers to be prime numbers, that is 2, 3, 5, you get an event. An event is any portion of a sample space. So in classical probability, given an event E of a sample space S, the probability of the event E is the number of outcomes in E divided by the number of outcomes in S. We assume in this case that S is a finite set. An event that has no outcome is called an impossible event, and it has probability 0. The sample space itself is called the certain event, and it has probability 1. Let's look at some example. A coin is tossed. What is the probability that you get a head? The number of possibilities is head or tail, which is 2. And in one of the outcome, we get head, so the probability is 1/2. Now, two dice are rolled. What is the probability that the sum of the two numbers is 3? What is the probability that the sum of the two numbers is 1? Or what is the probability that the sum of the two numbers is more than 1? On the next slide, we are going to look at each of these questions. So this diagram represents all the possible outcomes when you toss 2 die. So the outcome could be first die 1, second die 1, first die 1, second die 2, and so on as we get on this table. So we have a total of 36 outcomes, in which we are going to look for the outcome that has a sum of 3. 1 and 2 has a sum of 3. 2 and 1 has a sum of 3. So we have 2 outcomes with a sum of 3. So the probability of E, the sum is 3, is 2/36, which is 1/18. Now, if we want the probability for getting a sum of 1, we will see that none of the outcomes that we had on that table will have a sum of 1. So it's an impossible event, and the probability is 0. The question C is the probability that the sum of the two numbers is more than 1. Here we will observe that all of those numbers has a sum more than 1. So it is a certain event, and the probability is 1. So each time you have a question on probability, you want to know the number of outcomes in the sample space, and then what is the event and how many outcomes is in that event. Let's look at another example here. A coin is tossed 3 times. What is the probability that there is exactly 1 head? I'm going to use the whiteboard to explain how to work out this question. Here, a coin is tossed 3 times, and we want to know the possible outcomes. So the first time, it could be head or tail. Second time, head or tail. Head or tail. Head or tail. Head or tail. Head. So this tree diagram will help us to illustrate all the possible outcomes. So here we have head, 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 head. Tail, head, head, tail, head, tail, 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 head. So when you have a sequence of events, a tree diagram can easily be used to describe all the possible outcomes. And we can see here that we will have 8 outcomes. The question was, find the probability that there is exactly 1 head. The question was, find the probability that there is exactly 1 head. So here we have exactly 1 head, exactly 1 head, exactly 1 head. So the probability of exactly 1 head is 3/8. So there could be many other questions here. Whenever we have a situation where an experiment is a sequence of events, a tree diagram is an easy way to list all the possible outcomes. Complement of an event. The complement of an event is the set of outcomes of the sample space that are not in that event. It's like the opposite of that event. So we will observe here that if we have a sample space S and an event E, the number of outcome in S is the number of outcome in E plus the number of outcome in E complement. Using that, we can derive the complement rule of probability, which states that the probability of the complement of an event is 1 minus the probability of that event. Because each event is the complement of its complement, the probability of the event is 1 minus the probability of the complement. This rule is going to become very useful in computing probability in some situations in which it is much easier to use the complement than to find the probability of an event directly. Example, the probability that a college student who has not received a flu shot will get the flu is 0.45. What is the probability that a college student will not get the flu if the student has not had the flu shot? So because the probability of getting a flu without a flu shot is 0.45, the probability of not getting a flu will be 1 minus 0.45, which is 0.55. We are going to look in the next section on some probability rules for compound events. When we have events, we can combine them using disjunction and conjunction. So two events A and B are from a sample space. If two events A and B are from a sample space S, we can define another event called A or B. This event A or B will put together outcome in A and B, put them together, including outcome that are in both. For example, if we say that we want to mix two classes together, we put all the students together, maybe from Stat 205 and the class from maybe Biology 101. So it might happen that some student in both classes, it doesn't matter, so we combine them. When we say A and B, what we mean is the set of outcomes that are in both events at the same time. For example, if we take the numbers on a die, we can make A to be 135 and B to be 235. Then A or B will be 1, 2, 3, 5. That is putting A and B together. And A and B will be 3, 5. So in general, in probability, we are interested in knowing the probability of disjunction and conjunction, probability of A or B, and probability of A and B. So that is what we call the rules of, some additional rules of probability. Or will be for addition and will be for multiplication. When we think about event A or B, we can represent them on a Venn diagram, as you can see here. On this Venn diagram, where there is this intersection is A and B. So if we want to know the number of outcome in A or B, we will count the number of outcome in A, add the number of outcome of B, and then in doing so, we will be adding the intersection twice. So we subtract them. So a number of outcome in A or B is number of outcome in A plus number of outcome in B minus number of outcome in A and B. We use that to define the probability rule. The probability of A or B is probability of A plus probability of B minus probability of A and B. Let's look at an example here. A student club at a small college is made of junior and senior students. There are 13 juniors and 15 seniors. 8 of the senior students are female. If there are 11 males in the club, find the probability that a randomly selected member of the club is female, female and junior, female or senior. So I want us to work this out without looking at I want to reconstruct the table using the information which is here. We want to note here that there are 13 juniors and 15 seniors. 8 of the senior students are female, and there are 11 males in the club. Okay. So I'm going to make a table. There are juniors and seniors. We are discussing male and females. Based on the information that we have, there are 13 juniors and 15 seniors. Juniors, 13, seniors, 15. In addition, there are 8 of the senior students are female. Of the senior students, 8. Pardon? Is anybody speaking? Okay. So 8 of the senior students are female. So we write 8 here. And there are 11 males in the club. So we put 11 here. So these were the information that we had. If you look at the PowerPoint, I have already completed it, but I want us to also learn how to complete such a diagram. Here we will see we have a total of 28 members in the club. If 11 are males, then 28 minus 11 give us the number of females. That should be 17. So if 8 of the females are senior, then 9 are juniors out of 17. Now we can complete here. If of the juniors, 9 are females, then 4 are males. Of the seniors, if 8 are females, then 7. So this is how we can complete the table. Now the question we had was, what is the probability that a randomly selected member of the club is female? Probability for female will be, we have a total of 17 females divided by 28. The next question was, what is the probability that the student is female and junior? Probability for female and junior. Female and junior. So we will count the number of females that are junior. How many females are junior here? We have 9 females are junior. So this will be 9/28. The last question was female or junior. Probability of female or junior, which is probability of female plus probability of junior minus probability of female and junior, which is 17/28 plus junior is 13, 13 junior out of a total of 28 minus 9/28. Because they have the same denominator, we will do 17 plus 13, which is 30 minus 9, 21/28. Divide both by 7, 3/4. So on the PowerPoint, this is what you get. We call two events A, B mutually exclusive if they cannot occur at the same time. That is, A and B is impossible. A and B is impossible. For example, if A are even numbers and B are odd numbers, then A and B will be impossible. So the probability of A or B, if A and B are mutually exclusive, will just be probability of A plus probability of B. An example, a card is drawn from a standard deck. What is the probability that the card is a king or jack? The probability of king and jack is impossible. There's no card that is at the same time king and jack. So both events are mutually exclusive, and the probability of king or jack will be probability of king plus probability of jack, which is 8/52 equals to 4/13. So what we are saying here is that in some cases, when you have mutually exclusive events, you don't need to think about the and, because for mutually exclusive events, and is impossible. Conditional event is another form of expression of probability. So the probability of an event B, given that event A has occurred, is called the conditional probability of B given A, and is denoted by P of B bar A. And the probability of B given A equals to the number of outcomes in A and B divided by the number of outcomes in A, or the probability of A and B divided by the probability of A. Let's look at the example we just had. In that example, we had juniors and senior students in a club. And we may want to find the probability that a randomly selected member of the club is a male, given that the student is junior. If the student is a junior, we can find this probability just by counting the number of males that are junior. That is the understanding of conditional probability. We will look onto the table and we will see that there are 4 juniors that are male out of 13. And the probability of a male, given that the student is junior, will be 4/13. And I want to mention here, most of the time, you will have trouble about fractions on your quizzes. Generally, I use decimals because you can use calculator to get the decimal number. So most of the time, I prefer decimal numbers as answers, and I usually give you multiple choice. So you choose the number that is closest to the one that you have on your calculator. General multiplication rule. So I will explain this multiplication rule on the whiteboard. So we define the conditional probability of B given A as the probability of A and B divided by the probability of A. You saw that with that question of find the probability that the student is male, given that the student is junior. Just as I can ask you, a card is randomly drawn from a standard deck. What is the probability that the card is a king, given that the card is a club? You will just go among the club and count the number of king. So the conditional probability of B given A is probability of A and B divided by probability of A. So because of this, we can write that the probability of A and B is equal to the probability of A times the probability of B given A. This is what we call the general multiplication rule. Because in this expression of A and B, we can't tell whether A comes before B or B comes before A. We can write this again as probability of B times probability of A given B. I want you to observe that I'm not just changing A and B here, I am also changing the position of A and B in the conditional expression. For example, 2 cards are drawn one after the other from a standard deck without replacement. What is the probability that both cards are king? So we will say let K1 be the first card is king and K2 the second card is king. Then the probability of K1 and K2 will be probability of K1 times probability of K2 given K1. That is the probability that the first card is king times the probability that the second card is king, given that the first card was a king. So the probability that the first card is king is 4/52. There are 4 kings out of 52 cards. Now you have already picked 1 king and there are only 3 remaining. You took 1 card out and there are 51 remaining. So the probability of getting a king, given that a card was taken out as a king, will be 3/51. That's a conditional probability. So that is an application of conditional probability to get what we call multiplication rule. If you have a question, please stop me. In probability, we call two events independent if they do not affect each other in their occurrence. That is, the probability of one given the other does not change that probability, given that has no effect. For example, I will say that two students are independent if the fact that one is doing something does not tell you anything about whether another one is doing it or not. That is a little bit of what conditional probability independent event is about. Meanwhile, mutually exclusive event will be that they cannot be together at the same place. They cannot do their project together. They don't like each other. They are mutually exclusive. If you get into a party and you see one, you are sure the other one is not going to be there. That is mutually exclusive. Independent is that while the fact that you know something about one does not help you in any way to know anything about the other one. So in general, we say that two events are independent if probability of A given B is equal to probability of A. Let's go to the whiteboard and see the. So this is how we define conditional probability. Probability of B given A. Now, if A and B are independent, the given A will not matter, and the probability of B given A will remain probability of B. And the probability of A given B will remain probability of A, given that does not change. So in that reason, when two events are independent, we can define it again by saying that probability of A and B is equal to probability of A times probability of B. This is a property of independent events. Let's take this example. Two cards are drawn one after the other, now with replacement. What is the probability that both cards are king? So let's K1 be the first card is a king and K2 be the second card is a king. Now, probability of K1 and K2, if we think about what we wrote before, it will be probability of K1 times probability of K2 given K1. But the fact that the first card was returned, the probability of K2 given K1 will remain probability of K. So we will have 4/52 times 4/52. This is another example of application of independent events. It is known that 46% of high school students claim they take mathematics courses because they love mathematics. If 5 students are randomly selected, what is the probability that all love mathematics? None love mathematics. At least one of them love mathematics. Let's start with the first one, A. Because these 5 students were randomly selected, they are naturally independent of each other. For that reason, the probability here should be 3 students, not 5. Let me see what we get here. The fact that they love mathematics is independent of each other. So for that reason, the first student love mathematics, the second love mathematics, and the third love mathematics are independent events. So we will just multiply the probability through to get 0.46 times 0.46 times 0.46 equals to 0.097. Now, if we think about the probability that none love mathematics, it means none of the three. The first one does not love mathematics, the second one does not love mathematics, and the third one does not love mathematics. And because they were independently selected, the probability will be multiplying the complement probability through. So the probability that a student will not love mathematics is 1 minus 0.46, which is 0.54, raised to power 3, and we get 0.157. Now we will think for the Third question, at least one of them love mathematics. We will use the complement of at least one. The opposite of at least one is none. Think about it. At least one is 1, 2, 3, 1, 2, or 3. At least one is none. So the probability of none is the same as the probability we got in B, which is 0.157. We subtract it from 1 and to get 0.842. So you will have this type of questions at homework and quizzes where we have random selection of individuals, random selection of items, and you might want to think about the complement rule when you are using the expression at least. It's a summary of what we just said. Next section is counting rule. The fundamental counting principles state that if you have a sequence of events in such a way that there are n1 ways for the first event to occur, n2 for the second event, and nm for the mth event, then the probability that the sequence of events will occur will be n1 times n2 times nm. Example, Jacqueline is in a nursing program and is required to take a course in psychology and one in physiology. There are 2 courses in physiology, one A and B, next semester. She also wants to take Spanish too. If there are 2 sections of psychology, 2 of physiology, and 3 of Spanish, in how many different class schedules can Jacqueline choose from? Assume that the time of section do not conflict. So she can select any 2 of psychology, any 2 of physiology, and any 3 of Spanish too. So the number of ways will be 2 times 2 times 3 equals to 12. That's the application of the fundamental counting rule. We can use a tree diagram to illustrate this. Factorial notation. In expressing counting rules, often we need to multiply a number by all the number that comes before it. We use the factorial notation. For example, in how many ways can you arrange 10 individuals on a bench? There will be 10 ways to select the first one, 9 to select the second, 8 to select the third, 7, and so on. So the total number of ways will be 10 times 9 times 8 times 7 times 6, and so on. We call that factorial. 0 factorial is 1, and 1 factorial is 1. So in a permutation, objects are arranged in order. Just like I said, arranging 10 individuals on a bench. But sometimes we want to take like 3 objects out of 10. So in how many ways can we arrange 3 individuals from 10? There will be 10 ways to choose the first one, 9 ways to choose the second, and 8 ways to choose the third. So that is the number of permutations of objects. So the number of permutation of objects is denoted by P and R. I usually prefer the notation NPR. I will write it on the whiteboard. So let's say we have 7 students, and we want to choose 3 of them in a certain order. Maybe 1 to sing, 1 to dance, and 1 to watch. So there are some specific way of choosing. If I choose ABC, it will be different from BCA. So we will say there are 7 ways to choose the first, 6 ways the second, and 3 the third. We are going to write this as 7 factorial divided by 7 minus 3. Here is 5. Which is 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 factorial. And this is 4 factorial. So the general rule is NPR is equal to n factorial divided by n minus r factorial. On your calculator, you can use the probability formula to get the permutation rule. So if you have your TI-83 or T4 calculator, you can use it by going to math. We will get to that when we solve more problems. I'm skipping because it's what I just explained on the whiteboard. Combination is the arrangement of objects without considering order. I'm going to explain this on the whiteboard. So suppose I have 7 students and want to choose 3 of them to perform 3 different tasks. To do that, the number of ways to make the selection, I say it was, I said the number of ways to make this selection was 7 permutation 3, which is 7 factorial divided by 7 minus 3 factorial, which is 7 times 6 times 5. Now, in combination, order is not important. It means if I choose ABC, it is the same as ACB. It's the same as CBA. It's the same as CAB, and so on. So order is not important, meaning that if I am choosing 3 students just for them to go eat at Tovian, at a restaurant, then I can list them in any way. Because of that, there is a link between combination and permutation. So when we choose a combination of 3 objects, it can represent more than 3. It actually represents 3 factorial permutation. So we can write it again as BAC or BCA. So one combination represents 6 permutations. So there are more permutations. I'm sorry, there are more permutations of the same object of a combination. So the number of combination of 3 objects out of 7 is the number of permutation divided by 3 factorial. 3 factorial is the number of ways you can rearrange the 3 objects. So which will be 7 factorial divided by 3 factorial times 7 minus 3 factorial. Which is 7 factorial divided by 3 factorial times 4 factorial. So we can write this against as 7 times 6 times 5 divided by 6, which is 35. You can use your calculator. Any of you have a TI 83 or 84 calculator here? Anybody want to use a TI calculator at this point?
Mine is upstairs, but I can go get it.
Oh yeah, we will wait for you. I will get a glass of water to drink as well. We are almost done anyway. So with probability, calculator is very useful. So always come with your TI 83. Are you here?
Yes, I got it.
Okay, we are going to do 7 permutation tree and 7 combination tree. So you go to math, to the up top left part of your calculator, you will see second, alpha, then math. So before you click on math, click on 7 first. 7, then math, and then you will take your cursor to probability. 2 is for permutation. You click enter and write 3. Then you will have 7 permutation tree. Are you able to do that?
Can you explain that again? I got confused.
Okay. Let's start over. You press 7. We want to do 7 permutation tree. You press 7. Do you see math?
What am I supposed to look at?
Okay, press clear. Let's just start over. Press clear. Have you cleared everything?
Yes.
Now you are on, and we want to do 7 permutation tree. Okay?
Okay.
So now you enter 7.
Yes.
Then you will see the key, M-A-T-H. Do you see math, like mathematics?
Yes.
Okay, press that. Then you will see math, number, complex, and then PRB for probability. You take the cursor to PRB for probability. Then you press 2 for permutation, NPR, permutation. You press 2.
Okay.
Then you enter 3.
Okay.
So
thank you.
Once you do it 2 or 3 times, you will get used to it. You will not need it. It looks long the first time you are learning it. So the same thing we would have done for combination. For combination, you press 7, math, take the cursor to probability, press 3, and then 3, and you will have 35. So combination is generally used when order is not required. In your political science class, you are assigned to read any 4 books from a list of 10 books. How many different groups of 4 are available from the list of 10? Because you are just picking 4 books out of 10, maybe from a list, it is a combination because the order in which those books are used is not specified. So you will do 10 combination 4, which is 210. You can use your calculator to do that. Now, a box contains 6 red balls and 8 blue balls. 5 balls are randomly selected. What is the probability that there are exactly 3 blue balls? Here, 5 balls are selected. So the first thing to do is to find the number of ways to select 5 balls. The total number of balls here is 14. So we want to select 5 balls out of 14. So we will do 14 combination 5. Let's use the calculator to do that. So we enter 14, math, probability, enter 3 and 5. So you will get 2002. Next, you will have this type of question in your quiz or exam. You should be able to make the difference between selecting the number of ways in general and then selecting a number of ways with a specification. The second question is, the event is exactly 3 blue balls. Because you have 5 balls, when they say 3 blue balls, that means 3 are blue and 2 are not blue. So we want to know how to select 3 blue and 2 that are not blue, that are red. So there are 8 blue balls. We want to select 3. We will use 8 combination 3. And then there are 6 red ball, and we will do 6 combination 2. Multiply the two numbers to get the number of ways to select exactly 3 blue balls. Common mistake is that students only use 56, forgetting that 5 balls were selected. So there were 3 blue and then 2 red. Now, sometimes I ask you separate questions like this. When I ask separate questions, you have to, for example, I may give you this type of problem. A box contains 6 red balls and 8 blue balls. Find the number of ways of selecting 5 balls. So you don't need to do everything here. You just need to do 14 combination 5. I can say, in how many ways can you select 3 blue balls? When I say select 3 blue balls, when initially there were 5 balls to be selected, you need to remember that there will be 2 that are not blue. So you will think about in how many ways to select the 3 out of 8, and in how many ways to select the 2 out of 6. And now the probability, I can ask you, what is the probability that there are exactly 3 blue balls? It will be 840 over 2002. 2002, remember, is the sample space, the number of ways of selecting 5 balls in general. 840 is the number of ways of selecting 5 balls, given that, knowing that 3 of them are blue. With 3 of them blue, not knowing, with 3 of them blue. Okay, so this is it for today, chapter 4. You can do the homework for the 3 sections. If you have a question, don't hesitate to send me an email. I will respond to you. And if there is need, we can also make an appointment to meet on Zoom for me to explain to you. Remember, send me an email right from your first attempt as you are doing your quizzes. Don't wait until the 3rd attempt to tell me, I don't understand why I got this wrong, and then you cannot make any change. First attempt, send me emails. I will explain to you, and then you will take the 2nd attempt, and you will improve your score. Even if you get 2 on the first attempt, just take the other 2 attempts. It will help you to see many other type of questions.
Thank you.
You're welcome.
Thank you.
You're welcome. Thank you.